NASA's Perseverance rover just found something on Mars that shouldn't exist. A rock. Just a rock, sitting half-buried in a dry riverbed inside Jezero Crater. But when the rover's cameras zoomed in close, scientists saw something that made their jaws drop: dozens of tiny, irregular white spots, each one ringed with a thin halo of black material. Millimeter-sized. Scattered across the surface like a pattern you'd expect to find on an animal's hide, not a chunk of Martian mudstone. They nicknamed it leopard spots. And here's the part that should give you chills: on Earth, this exact kind of spotting is almost always the fingerprint of one thing: chemical reactions that microbes use to survive. Not always, but almost always. So the question NASA's own scientists are now wrestling with, in a peer-reviewed paper, in front of the entire planetary science community, is this: did we just photograph the chemical leftovers of alien life? Or is Mars simply playing an extraordinarily convincing trick on us? Stick with me, because this is not science fiction. This is a real rock, with a real name, Cheyava Falls, sitting in a titanium sample tube on the surface of Mars right now, waiting for a ride home. And by the end of this video, you'll understand exactly why NASA's acting administrator stood in front of reporters and called it possibly the clearest sign of life we have ever found beyond Earth. Let's get into it. Before we get to the rock itself, it's worth understanding exactly what Perseverance was sent to Mars to do, because this discovery didn't happen by accident. It happened because a machine built specifically for this job was finally doing its job. Perseverance touched down on Mars back in February 2021, targeting one very specific location, Jezero Crater. NASA didn't pick this crater randomly. Orbital images had shown, for years, that Jezero had the unmistakable shape of an ancient river delta fanning out into a crater basin, the kind of formation that, on Earth, only forms when a river has been steadily dumping sediment into a standing body of water for a very long time. If Mars ever had a lake capable of supporting life, this was one of the best candidates in the entire solar system. The rover spent its first years on the crater floor, studying volcanic rock, before climbing up into the delta itself and confirming, layer by layer, that yes, this was in fact built by flowing water the same way deltas form here on Earth. From there, Perseverance pushed further, into a strip of terrain called the Martian unit, and eventually down into a river channel carved into that terrain, the channel that fed the delta with sediment in the first place. That channel is called Neretva Vallis. And it's inside the walls of Neretva Vallis, in a formation the team named Bright Angel, where Cheyava Falls was sitting, half exposed, waiting to be noticed. None of this was luck stacked on luck. It was a rover, engineered specifically to hunt for ancient signs of life, deliberately tracing the path water would have taken billions of years ago, in the exact kind of environment scientists have long believed gave life its best shot on Mars. The team happened to plan a drive down into that river channel right before pivoting back up toward the crater rim, and that one decision put them face to face with what may be the most important rock this rover has ever touched. With that context in place, let's break down exactly what the rover found. To understand why one rock has the astrobiology world holding its breath, you have to go back to July 2024, deep inside Mars' Jezero Crater, a 28-mile-wide basin that scientists are almost certain used to be a lake, fed by a river delta, roughly 3.5 billion years ago. Perseverance had already spent years crawling across the crater floor, climbing the ancient river delta, and skirting the crater rim. But on Martian Day, or Sol, 1212, July 18th in Earth years, the rover's robotic arm reached out and photographed a rock that would change the entire trajectory of the mission. They called it Cheyava Falls, named after a waterfall in the Grand Canyon. It's not a small rock either, about 3¼ feet long and 2 feet wide, roughly the size of a large coffee table, wedged into the wall of what used to be a river channel called Neretva Vallis. At first glance, it doesn't look like much. Running down the length of the rock are thick white veins, bands of calcium sulfate, a mineral that forms when water carrying dissolved salts flows through cracks in rock and then evaporates or precipitates out. Between those white veins sit reddish bands of material, and that rusty color comes from hematite, the same iron oxide mineral that gives the entire Martian surface its famous orange-red hue. None of that, on its own, is shocking. Mars is red because of iron oxide. Veins of calcium sulfate have shown up elsewhere on the mission. What stopped the science team cold was what was sitting inside those reddish bands. Scattered across the red material were dozens of small, irregularly shaped light-colored patches, some just a fraction of a millimeter across, some closer to a millimeter or two, and every single one of them was wrapped in a thin, dark ring. The science team started calling the smaller version of these features poppy seeds, and the larger, more dramatic ones leopard spots, because visually, that's exactly what they look like, a pale patch of rock with a dark outline around it, repeating across the surface like a pattern on an animal's coat. Why did that trigger alarm bells? Because on Earth, this specific kind of spotting, pale, bleached centers ringed by dark material inside a red, iron-rich rock, is a textbook signature. Geologists have seen it for decades in sedimentary rocks here on Earth, and in almost every case, it's the product of a chemical reaction that strips color-giving iron oxide out of the rock and deposits new minerals in its place. Sometimes that reaction happens through pure chemistry. But very often, on Earth, it happens because microbes are doing the work, literally eating organic matter and using the iron in the rock as part of their metabolism, leaving these bleached, ringed scars behind as a byproduct. So the rover's own cameras had photographed a pattern that, statistically speaking, is usually associated with biology back home. That alone was enough to get every astrobiologist on the mission leaning forward in their chair. But the visual pattern was only the opening act. What came next, from Perseverance's onboard chemistry instruments, is what turned a curious rock formation into what NASA now calls its strongest potential biosignature ever found on Mars. Here's where the story moves from interesting rock pattern to possible biosignature, and it happens because Perseverance isn't just a camera on wheels. Bolted to the end of its 7-foot robotic arm is an instrument called Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals, paired with a high-resolution camera called Watson. Right next to it sits another instrument called PXL, which maps the chemical composition of rock surfaces at a microscopic scale. Together, these two instruments went to work on Cheyava Falls, and what they found inside those leopard spots reads almost like a chemistry class in how living systems generate energy. Let's start with the smaller, poppy seed features, because understanding them is the key to understanding everything else. Under PXL's microscopic gaze, these turned out to be tiny nodules, somewhere between 100 and 200 microns across, thinner than a human hair in some cases, made of a mineral cocktail rich in both iron and phosphorus. Based on their chemical signature, the science team's best guess is that these are a mineral called vivianite, an iron phosphate that also carries water molecules in its structure. Now here's the part that matters. Vivianite doesn't just appear out of nowhere. Its presence tells you that a specific kind of chemical reaction took place, a redox reaction, meaning a transfer of electrons between two substances. In this case, the iron in the surrounding red mudstone started out as ferric iron, the oxidized form, the stuff that makes Mars rust-colored in the first place. But inside these poppy seed nodules, that iron had been reduced, stripped of an electron and converted into a different, more reactive form, which then combined with phosphorus to form vivianite. Something had to donate the electrons that drove that reaction. And the leading candidate, according to the mission's own lead scientist, is the organic carbon sitting right there in the same mud. That's the headline discovery from Sherlock. It detected genuine organic compounds, carbon-based molecules considered the basic building blocks of life, embedded in the rock, and specifically a signal known as a G-band, a spectroscopic fingerprint associated with complex, high molecular weight carbon structures. In plain terms, this isn't a trace of one stray carbon atom. It's a signature of complicated, chunky organic molecules baked into the sediment. So put the two pieces together. You've got organic carbon in the mud. You've got iron oxide in the mud. And you've got clear mineral evidence that at some point, those two things reacted with each other, with the iron getting reduced and the carbon getting consumed. On Earth, this exact pairing, organic matter and iron oxide swapping electrons in a muddy, low-oxygen sediment, is one of the most common metabolisms microbes use to survive in places like lake beds, river deltas, and marine sediment. Bacteria that breathe iron instead of oxygen do this constantly, all over our planet, leaving behind exactly this kind of mineral fingerprint. Now zoom out to the larger leopard spots, because they tell an even more layered story. Under close analysis, each leopard spot turned out to have a kind of internal structure, almost like rings on a tree stump. The dark outer rim is made of that same vivianite, the iron phosphate. But the bleached, pale interior of the spot contains something different, a mineral called gragite, an iron sulfide. Gragite is the more provocative find of the two, and here's why. Producing gragite requires a reaction between sulfate and organic matter, essentially, sulfate-reducing chemistry. And on Earth, at the low temperatures we're talking about here, nowhere near boiling, just regular cool sediment temperatures, that particular reaction is agonizingly slow when there's no biology involved. So slow that scientists studying modern Earth sediments essentially never observe it happening abiotically at these temperatures. The two places it reliably happens fast enough to matter are inside hydrothermal systems cooked to well over 200 degrees Fahrenheit, or inside the metabolism of sulfate-reducing microbes, which use this exact chemical pathway to generate energy for themselves in oxygen-poor mud. So the chemical blueprint sitting inside Cheyava Falls looks like this: organic carbon, check. Iron reduction, check. Sulfate reduction producing an iron sulfide mineral that normally needs either intense heat or living organisms to form quickly, check. And crucially, when the science team went looking through Perseverance's other instruments for any sign that this rock had ever been heated to those extreme hydrothermal temperatures, they came up empty. Within the limits of what a rover parked 140 million miles from home can measure, Cheyava Falls does not look like it was ever cooked. Take away the heat explanation, and you're left staring at a chemical signature that, on Earth, we associate overwhelmingly with living microbes quietly metabolizing in ancient mud. That doesn't prove biology built these spots on Mars. But it's exactly why this rock jumped from interesting to the strongest potential biosignature the mission has ever produced. Now, if this were a courtroom, this is the part where the defense gets to speak. And credit where it's due, the Perseverance team didn't just get excited and run to the cameras. They spent well over a year hammering their own discovery, trying every way they could think of to explain these leopard spots without invoking biology at all. Why be so cautious? Because geology has a long history of playing tricks that look exactly like life. Scientists call this geological mimicry, mineral processes that produce shapes, patterns, or chemical signatures that are visually or chemically indistinguishable from something biology would make. It has burned researchers before, both on Earth and in the search for life beyond it, and nobody on this team wanted to be the group that announced alien life and then had to walk it back 6 months later. So what are the leading non-biological explanations, and how well do they hold up? The first and most obvious contender is heat. On Earth, when sulfate-rich water and organic-rich mud get cooked at high temperatures, generally above roughly 250 degrees Fahrenheit, you can force sulfate to react with organic carbon fast enough to produce iron sulfide minerals like gragite completely without any biology involved. This is the same basic chemistry that happens inside deep hydrothermal systems, the kind you find near volcanic vents or buried magma bodies. If Cheyava Falls had ever been baked by nearby volcanic heat, or by a buried intrusion of molten rock, that alone could potentially explain the gragite without needing a single microbe. Here's the problem for that theory: the evidence just doesn't support it. When the science team scoured the rock and its surroundings for any telltale sign of past heating, mineral changes, textures, alteration patterns that show up when rock gets cooked, they came up empty-handed. That doesn't rule out heating entirely. A rover's instrument suite has limits, and it's possible the rock was heated in a way current instruments simply can't detect from a distance. But based on everything Perseverance can currently measure, there's no direct evidence this rock was ever exposed to the kind of temperatures needed to drive that reaction abiotically. The second thread of the debate revolves around two other minerals found nearby, olivine and sulfate crystals. Olivine is a mineral that typically forms directly from cooling magma, in volcanic or igneous rock, and it's notoriously reactive when exposed to water. It tends to weather and break down quickly in wet environments. Finding olivine grains scattered near Cheyava Falls tells scientists something important about the broader environment. It suggests episodes of igneous activity in the region, meaning volcanic material was present and being weathered down, contributing sediment to the river system that eventually deposited this mud. The thick calcium sulfate veins threading through the rock tell a related, but distinct, story, one of water repeatedly moving through cracks in the rock, carrying dissolved minerals, and then precipitating them out as the water evaporated or as conditions changed. That points to multiple episodes of fluid movement through this rock over time, not just a single, simple wetting event. Put together, olivine and sulfate complicate any simple story. This wasn't a static, single chemistry environment. It was a dynamic system, volcanic material weathering down, water moving through cracks and pulses, minerals precipitating and dissolving over what was likely a long stretch of time. And in a system that complicated, there are more variables that could, in theory, conspire to produce something that merely resembles a biosignature without any life ever being involved. This is exactly why, when NASA's own peer-reviewed paper on Cheyava Falls was published in the journal Nature in September 2025, the team's language was careful, deliberate, and notably restrained. They didn't claim to have found alien life. What the lead author of that paper has said publicly is that after exhaustively testing every abiotic explanation the team could construct, they simply couldn't find one that fully accounted for everything they were seeing, not that no explanation exists, but that none of the ones tested so far fit as cleanly as a biological one would. That distinction matters enormously. Scientists use a tool called the Confidence of Life Detection Scale, or COLD scale, to communicate exactly how confident a claim like this really is, using a set of defined steps rather than a simple yes or no. According to the mission's lead scientist, Cheyava Falls currently sits at around step 3 of that scale, meaning the signal is real, contamination has been ruled out as an explanation, and the geological setting is a genuinely plausible habitat for ancient biology. But step 4, the step that requires ruling out every known non-biological process, has not been reached. Not because the team stopped trying, but because doing so with total confidence may be impossible from 140 million miles away, using only the instruments bolted to a rover's arm. One more detail from the investigation adds weight to the biological explanation, and it's easy to miss if you're not paying close attention. Organic carbon wasn't found evenly across every rock in the Bright Angel Formation. It showed up strongly in Cheyava Falls and in a nearby target called Apollo Temple, but it was essentially absent in another nearby target called Masonic Temple. If this organic signature were just some uniform background contamination, or a simple mineral coincidence baked into the whole formation, you'd expect to see it everywhere in roughly equal amounts. Instead, it's patchy, concentrated in specific rock types and largely missing from others. The leading explanation for that patchiness actually strengthens the case that something environmentally meaningful was happening. Cheyava Falls and Apollo Temple are both extremely fine-grained mudstones, the kind that form when mud slowly, gradually settles out of still water over long stretches of time, and slow, gradual settling gives any organic matter drifting down through the water column time to accumulate and get buried before it breaks down. Masonic Temple, by contrast, is a conglomerate, coarser rock deposited quickly, likely from a sudden debris flow rushing in off the crater walls. A rapid, chaotic deposit like that simply wouldn't give organic matter the same slow, steady window to accumulate. In other words, the presence or absence of organics tracks neatly with how patiently each layer of mud was laid down, which is exactly the kind of pattern you'd expect if the organic carbon reflects a real environmental process rather than random contamination or coincidence. That's precisely why the entire scientific community, cautious as it is, remains this excited. A rock that can't be easily explained away, examined by a team that tried its hardest to explain it away, is exactly the kind of result that pushes a mission forward instead of quietly fading into a footnote. For years, when people talked about the search for life on Mars, the conversation almost always centered on the surface, dusty red plains, dry riverbeds, ancient lakebeds baked by radiation and starved of atmosphere. Cheyava Falls forces a different kind of conversation entirely, one that shifts the spotlight underground, into the groundwater systems that once moved silently through Martian rock billions of years before Perseverance ever landed. Here's the environment scientists have reconstructed. Roughly 3.5 billion years ago, Jezero Crater held a lake, fed by a river delta pouring in from outside the crater rim. Perseverance has spent years documenting that delta, confirming, layer by layer, that it formed almost exactly the way river deltas form here on Earth, water flowing in, sediment dropping out, layers building up over time. But Cheyava Falls wasn't found in the delta itself. It was found further along the rover's path, in the walls of a river channel called Neretva Vallis, a channel that appears to have once fed sediment into that delta system. And the mudstone there turned out to be surprisingly fine-grained, almost too fine-grained for a fast-moving river channel, which usually deposits coarse sediment and lets the finer mud drift further out into open, still water. The team's leading explanation is that this particular channel may have gotten dammed up at some point, perhaps by a landslide, causing water to back up and slow down enough that fine mud could settle out and accumulate right there, layer after layer. That mud carried something else with it too, a chemical signature unlike anything else the mission has found lower down in the delta. This material was heavily oxidized and had been chemically stripped of elements like magnesium and calcium, a telltale sign of prolonged weathering, likely from rainfall or groundwater leaching through exposed rock somewhere outside the crater before being washed down into this channel. In other words, this mud had a complicated journey, weathered on land, transported by water, and finally settled into a still, muddy pocket where it could sit undisturbed for a very long time. That undisturbed pocket is exactly the kind of setting astrobiologists get excited about, because it checks off the three ingredients considered essential for life as we understand it: liquid water moving through the system for an extended period, organic carbon molecules present in usable form, and an energy source capable of sustaining metabolism, in this case the redox reactions between iron, sulfate, and organic matter described earlier. This is what scientists mean by a habitable niche, not the entire planet needing to be hospitable to life, just one small, localized pocket where the right chemistry concentrated long enough to matter. Cheyava Falls appears to be the first single spot in the entire mission where all three of those essential ingredients, water, organics, and energy, have been confirmed together in one place. Not just water. Not just organic carbon. All three, stacked in the same few centimeters of ancient mud. And the mechanism connecting all of it together is liquid water itself, acting as the medium that let these chemical reactions happen at all. Without water moving through those muds, iron couldn't have been mobilized and reduced, sulfate couldn't have migrated to react with organic carbon, and none of these reaction fronts, the poppy seeds, the leopard spots, could have physically formed. Every one of these mineral features is essentially frozen evidence of chemistry that needed liquid water as its stage. That's the real pivot this discovery represents. It's not just Mars had water once, which we've known for years. It's Mars had a specific pocket of underground, water-soaked mud with the exact chemical ingredients needed to support microbial metabolism, and we may be looking directly at the fossilized chemical residue of that process. Whether biology actually did the work remains the open question, but the environment itself has now graduated from merely wet to genuinely habitable, in the fullest sense scientists use that word. So where does this leave us? With a rock that scientists can't fully explain through geology alone, sitting inside a titanium tube nicknamed Sapphire Canyon, parked on the surface of Mars, roughly 140 million miles from the laboratories that could finally settle the question. And that gap, between what a rover can measure and what a laboratory on Earth could actually prove, is now the single most urgent problem in NASA's entire Mars exploration program. Perseverance's instruments were genuinely built to search for this kind of signal, and by every account, they performed exactly as designed. But a six-wheeled robot with a robotic arm, running instruments the size of toasters, can only take you so far. To go from, "we can't rule out biology," to, "we found evidence of biology," or, "we found evidence against biology," scientists need atomic-scale tools that simply cannot be shrunk down and bolted onto a rover. The kind of analysis researchers are hoping to run once, if this sample reaches Earth, includes things like isotopic analysis, comparing the precise atomic signatures of iron in the surrounding mud against the iron locked inside the vivianite and gragite minerals. Biological processes tend to leave distinctive isotopic fingerprints, subtly different from purely chemical reactions, and researchers want to run that same comparison across iron, sulfur, and multiple forms of carbon in this one rock, cross-checking each system against the others to see if they tell a consistent story. That kind of precision measurement across 3 different isotope systems in a single sample is simply beyond what any current Mars rover carries. This is exactly why the Mars Sample Return Program, NASA's ambitious, complicated, and at times politically contentious effort to physically bring Martian rock samples back to Earth, has taken on new urgency. Perseverance has already been caching sample tubes across Jezero Crater for years, patiently building an archive of Martian material for a future mission to retrieve. Cheyava Falls, cored into the Sapphire Canyon sample, is arguably now the crown jewel of that entire cache, the single tube that could plausibly contain the first direct physical evidence of ancient life beyond Earth, or conversely, the tube that finally, definitively demonstrates just how convincingly geology alone can imitate biology. Beyond the fate of this one sample, Cheyava Falls has already reshaped how NASA thinks about the hunt for life across the solar system. For years, the guiding strategy was almost entirely about finding the right broad environment, follow the water, find an ancient lakebed, land a rover nearby, and hope. Cheyava Falls demonstrates something more precise, that within a broadly promising environment, the real signal might be hiding in a handful of millimeter-scale mineral anomalies, invisible from orbit and easy to drive right past if a rover's cameras and chemistry instruments aren't sharp enough to catch them. That's a genuine shift in how future missions will be designed, not just choosing landing sites based on where water once flowed, but building instruments capable of zooming in on exactly this kind of small-scale chemical anomaly, wherever it turns up, whether that's on Mars, an icy moon like Europa or Enceladus, or somewhere we haven't even sent a spacecraft yet. For now, the honest answer to, did we find alien life, is still, we don't know. What we do know is that a team of scientists spent well over a year trying to disprove their own most exciting result, and the abiotic explanations they tested didn't fully hold up. That's not proof of life. But it's the most compelling, most rigorously tested candidate biosignature Mars has ever produced, a rock that may be quietly holding the answer to one of humanity's oldest questions, waiting patiently in its titanium tube for a ride home. Whether that ride happens soon depends on funding decisions and mission timelines still being worked out here on Earth. But the case for making it happen has never been stronger. Because right now, sitting on the surface of another planet, there's a fist-sized piece of rock that might be the closest thing we've ever found to a fossil of alien life, and the only way to know for sure is to bring it home. And it's worth remembering that Perseverance isn't finished. The rover is still out there right now, still driving, still drilling, with several sample tubes left to fill before its core mission wraps up. Cheyava Falls may be the headline discovery so far, but the team has been clear that they don't consider the search over. Every new outcrop is a chance to find another bright angel, another Sapphire Canyon, another piece of the puzzle that either strengthens or undercuts the case for ancient Martian life. That's the story of the Leopard spots on Mars. Not proof. Not fiction. Just the most tantalizing chemical mystery humanity has ever pulled off another world, and the beginning of a very real race to finally answer it. If you found this as fascinating as I did, let me know in the comments. What do you think is really etched into that rock? And stick around, because when Mars Sample Return finally gets a launch date, you'll want to be here for it.